Okay, so did everyone get the little thing? Okay, cool.
Yeah.
Okay, so I thought that today I would start with just a little presentation going over some basic stuff and then do, so for the first half and then the last half do a little more interactive tutorial type thing. And yeah, feel free to interrupt with any questions you have. And sorry if this is basic for those who know more about R, but hopefully something will be helpful. Cool, okay. Can you see this? Cool, okay. So my first slide is my favorite, if I can get to it. This is me explaining why I think a Bayesian mixed effect cumulative logit model is the best choice, and my friend who just wanted to know how to do a t-test in R, which I feel like is exactly my life. And I retweeted this on Twitter and it got like 1 like, so that's cool. Okay, so why use R instead of using like, SPSS or JAS for Stata or something a little more user interfacey? Well, firstly, R is like super flexible. So you can use multiple packages designed by different people with a bunch of functions in them. And then eventually you can even kind of create functions and packages yourself so that you can analyze and organize things exactly the way you want it. R is also really good at data wrangling, which some of you might know what I mean. I mean, like, when you get a data set and it's like a total mess and like your variables in like wide format, you need it to be in long format, or it's not like, I don't know, it's not calculated correctly. It hasn't been transformed. You have a bunch of people in there you need to exclude, stuff like that. And I feel like SPSS and JAS and all those things are really bad at that kind of data manipulation. And R is actually really good at that once you learn how to use it. So that's really useful. It's also really easy to like centralize everything that you do. So you can clean, score, analyze, make figures, make tables, write manuscripts, and even make presentations like this all in R, which is super helpful because as many of you also probably know, going back and forth from like a Word document to a script whenever your data changes can be really tedious. Also, it's really reproducible. So you're not pointing and clicking at on anything. So it's really easy to know exactly what you did, redo it again. And then it's also super easy to publish your code for other people to look at, to review, and also to run themselves. And I think one of the coolest things is that if you get new data or you get more data or you have to exclude data, you can basically just rerun all your analyses instantly with that new data just by feeding it into the script that you have. And then also once you use R, like over the course of time, you kind of end up doing a lot of the same things with the data that you did with a previous data set. And so you can kind of make your own like code repository where you have like, this is how I like simulate data. This is how I clean this thing. This is how I like subset certain things for scoring. And then you can use the same code over and over again with minor changes based on your data set. And if it's exactly the same, like you ran the study multiple times, you can literally just run it through the exact same script, which is super nice. Okay, so now just some of the basics. So if you don't have it, and I will also send you guys these slides and some more material, so don't worry about following along. I think it's like kind of harder to do that at first. So you can download R here at this link, and then RStudio. And I'm going to send you guys a guide, which will tell you kind of step-by-step instructions too, if you're confused, because there's a few things that you have to do about choosing your nearest location as a mirror and things like that. But basically, R is like the software that runs in the background. So you're not really ever going to open just R or use just R. You're going to use RStudio, which is kind of like, if you think of like almost like Word, like how Word has this nice like interface for you to type stuff into and like do stuff with, but you're not really like dealing with the raw like HTML or unformatted text code kind of analogy. You'll see more what I mean when we kind of start going through it. So this is your RStudio environment. And so the first thing I'll do is just talk about these different kind of, can you see my mouse? Okay, these different kind of spaces. So this is, I think it's called the source pane technically. It's like where you would open up any kind of script that you're wanting to run, or any kind of, it's almost like your document kind of pane. Then you have this area, which is your environment. So when you create different objects or you load in data, it will show up here with a few little bits of like information about it. There's a few other things here, but not as important really as this environment thing. Your console is like your main actual, it's like the machine of R. So like if you've ever opened up your terminal on your computer, like on your Mac, and run like Python code or any kind of other code, that's basically what this is. So you can execute things here, but they don't really save. So you're going to want to save anything that you're doing here, and then click run or click command enter. I think there's keyboard command shortcuts to run the code, and that basically runs it here. But if you just run it here, it won't save like later if you leave R. And then here, which is like a few different things. So you have like files, and this is kind of just all the files that are in the whatever folder or directory you're looking at the time. Sometimes plots show up here, and then you also get some help panes and packages and things there. Okay, so like I said, you can type and execute code from the console, but to save it and come back later, you want to use a script. So the first thing that you should do is basically make an empty folder on your computer where you're going to put your data, your script, and your code. And then you're going to just open RStudio, click File, New File, and then I recommend an R Markdown script to write all of your analyses in, and we'll see that in a minute. You can also just use a regular R script, but the Markdown it's a little more complicated, but has quite a few advantages, which I think are useful. So one of them is, so what's a working directory? So I think this was really confusing to me when I first started using R. I was like, where is it like pulling things from? I don't understand. So when you open R, you basically have a working directory. And if you type in the console, get working directory in these two parentheses and click enter, it will tell you kind of what directory you are working in right now. So in this case, it was just in my main user folder. And so that's important because if you're reading in any kind of data or any kind of files, it's going to automatically read it in relative to your working directory. So you're going to want to, like say I had a file in here in a folder. To access that file, I would need to put a slash for the folder name, and then the file name. Whereas if the file was just in my working directory, then I just need to put the file name. So you'll see this a bit more too when we go in the tutorial part, but the benefits of using an R Markdown is that it automatically sets your working directory to whatever folder it's in. So like if I had this script here sitting in this tutorial folder, it would automatically set this folder as my working directory so that I don't need to worry about the absolute path to my files, which is really helpful. Okay, another thing I found really hard when I first started was thinking about object-oriented programming. And if you've never done any kind of computer science, I think this is kind of a complicated concept. So basically, the way that you can think of programming in R working is that you create these different objects and you store them in the computer's memory. So here, and this is you create an object using, you can either use an equal sign or you use a little, I don't know, this thing's called caret thingy and a dash. And that basically means I'm assigning 2 + 1 to this thing that's I've named an object, right? So an object is 2 + 1. And so then if I assign that and then I run this code, it gives me this output 3, which is 2 + 1. This is how our output looks. This is just how, I think this just refers to a line, like if you had multiple lines. So you can kind of ignore these two parts, and this is your output. So in addition to storing it in the memory, it also shows up in your environment in RStudio. So that's where you can see that if you create an object, it kind of shows up in this right-hand pane of your computer, of your RStudio, showing that I have an object in there and it's 3. So then you can do other things with it. And this is really good when you have complex things like big data sets. So if I wanted to create another object, 10, then I could create an object that's the sum of those objects and just add them together by referencing their name only. So then if I run the sum of objects, I have 13, which is 10 plus 3, which was the previous object was 3. Does that make sense to everyone? Does anyone have any questions on that? Because it's kind of an important, like, basic bit of R. Good, cool. Okay. And then there's a few data types, which can also give you some problems if you're trying to perform different like operations and you want to like add or subtract things. And so it's important to kind of understand what types of objects there are, and then data types, and then also how to find out. So you can have numeric data, which is numbers. You can have integer data, which is numbers, but whole numbers. You can have characters or strings, which is like strings of text, basically. You can have logical, which is true, false. And then you can have factors, which are like factor variables that you would think of in a study. It might be like sex is male, female, or like year of education. Could be like an undergraduate, a postgraduate, a postdoc, you know, something like that. And so the way that you find out what type of object you're working with is you type this class and then the thing that you want to find out what it is. So if I type class sum of objects, then I can find out that it's numeric. And that's helpful if R is throwing you an error that's like, I can't add these two things together because you can't add strings together, basically. You can't add words together. So if for some reason it was classifying your integer or your numeric variable as a string, it would throw you an error, and that could be a basic way to kind of solve that. Okay, so in addition to data types, there are like data structures in R, and there's a couple, but we'll just mainly be talking about data frames because I think that's the most relevant for research. Okay, so let's make our own. So each one of these lines can be thought of as a vector, basically. And a vector is kind of just like a list. It's not really a list because there's another thing called a list, but let's use this as an example. This C means concatenate, but you can kind of think of that as just combine. So I want to combine, I want to make a list of 16.5, 21.4, and these are the ages of all my participants. So let's say I have 5 participants. These are the ages of each one. I'm just making this data up. This is just for this example. So the first thing I'm going to create is participant IDs, basically. So I have participant ID 1, 2, 3, 4, 5. And kind of similarly to what I was talking about before, these are basically placeholders for names, right? Because we don't put participant names in the file. So it's not a number. So you want to make sure that R knows it's not a number. So we put as factor, and then we combine this list of numbers. And so then it treats these as if they are names. Okay, so then we want to enter, so we have participants 1 through 5. Then we want a list of their sexes. So we have a list of, and the way that you designate that something is a string is in quotes. And you can use single or double quotes. Sometimes it can be easier to use one or the other based on like how the other things you have in your statement. So you just make a list of, so 1, 2, 3, 4, 5. Those are your 5 sexes. And then just for an example, there's, say they took 2 tests, like these were 2 tests over the course of a term. So you have score 1 and score 2. And so like say these are test scores from the midterm and test scores from the final. I don't think you guys have midterms or finals, but we do. Anyway, and then you can combine these all. So these are basically just, think of this as kind of being one column, right? So, and that's a bit confusing because it's set out horizontally. So you kind of think of it as a row, but you actually want to think of it as a column. So this is a column, this is a column, this is a column, this is a column. And you can combine these into a data frame by using column, which is the C, bind.data frame. And then you just call each of these vectors that you've created. And then it creates this nice data frame for you of your 5 participants, their sexes, their ages, and their scores. Does that make sense to everyone? Cool. So another thing that's really useful is indexing, and I feel like I didn't learn this for a really long time, and it was pretty simple and actually really helpful. So say I want to know what my third participant's score number 1 was, right? So what I want to do basically is I want to use these square brackets to call that observation in that cell. So you can think of this as like a cell, and the first one is the rows and the second one is the columns. So if I want to find out what the third, so that's participant 3 and column 4, 1, 2, 3, 4. By the way, these are just row numbers on R, so you can kind of ignore those. 1, 2, 3, 4, 73. If I want to call that, I would just put the data frame in question, the row number, and the column number, and it will give me that observation. So it'll give me the value in that cell, basically. I also think it's really helpful to know how to add variables. So say I want to create a different score between score 2 and score 1. So say score 2 was the final and score 1 was the midterm, and you want to see if the students got better from the midterm to the final. So the way you do that is you basically call the data frame, then you use this $sign, and the $sign basically means add a variable called this to this data frame. So add a variable called difference to this data frame. And then I'm going to tell it what I want this variable to have in it. So in this variable, I want to have data frame score 2, and that's the way that you call, it's the way that you call these variables from this as well. So when it's on this side of the operator, it's creating a variable. When it's on this side, it's kind of like grabbing that variable from the data set. So I'm going to grab score 2, and I want to subtract score 1 from score 2. And then it's basically created this variable in a new column. So I didn't show you, but it would basically be a column that's right here that says difference. And that would have all 5 of your differences. So you can see that everybody improved except this person who got 1 point lower on their score 2 versus score 1. And it's really nice because instead of having to actually subtract each thing, you can just put this, and it does these like row-wise operations. So it treats every row, every participant as its own like row, and then does that operation on each one, which is really helpful. Okay, then you can get some summary statistics doing some really easy functions like mean. If you want to find the mean of the age, so you do the same thing where you just type mean, the data frame, and then call on the variable that you want with this $sign. So you can see the mean age is 18.7. The range is 16.5 to 21.4. And then if you want to find what variables you have in a factor, you type this, which is called levels. So you levels, and then your data frame, call your variable, and then it shows you what you have, what groups you have basically. So you have female and male in this data set. Okay. One other really useful thing is, say I want to know what the average score is just for the females in the data. So the way that you would do that is, I know this looks confusing at first, but it's pretty straightforward. So you'll call the mean, you'll call the data frame and the variable you're interested in. So I'm only interested in score 1. And then you use these brackets to basically specify a condition that you want to find the mean score 1 of. So in this case, for this data frame with sex equals female, you want to find the mean of their score 1s. And also important, you have to use equals equals for conditional statements like this, because equals is also an assignment operator in R. So instead of using the little caret dash thingy, you could use equals. So to not be confused, R makes you put equals equals for what we would think of as equals. Does anyone have any questions? Cool. Okay. So you can see the same thing here. So if you want to find the mean for the males in the sample, you would just do the exact same thing. Wait, I'm going to move you guys over and see if I can see you all at the same time. Hold on. Oh yeah, okay, cool. Okay, I can see you guys all at the same time now, which is nice. Okay. If you want to find the male's mean, you just type male here for your condition that you want to find instead of female. Okay. Oops. So inferential statistics. So inferential statistics in R is really surprisingly easy after all of the data wrangling and the data manipulation and everything. So say we wanted to know if females in this sample have statistically significantly higher test scores on score 1 than males. So basically you call this t-test function. You type in the data frame, you call the variable that you're interested in, and then this little thing, it looks like a dash, but it's actually a tilde. And that means basically you can think of that as predicted by or grouped by. So you can think of what's the difference in score 1 as predicted by sex. So it makes a little more sense when you're thinking of regression and correlation, but you can also just think of this as grouped by sex. So what's the difference between score 1 as grouped by sex? So then this is the output, and it seems like a lot, but it's actually also pretty straightforward. So it basically here tells you the mean group in the group female, which we also found out earlier when we just ran our quick summary statistics. And then it tells you the mean of group male. Then it gives you the T statistic, your degrees of freedom, and this is adjusted degrees of freedom because it's a Welch's two sample t-test, which I'm guessing means the variance between males and females wasn't equal, which it does that automatically. And then your p-value. So it's obviously a very large p-value. So we can't say that for certain that there's any difference between the two groups. And this is the one other thing I will say is this, it also gives you the confidence interval, which is kind of nice. It's a little bit less intuitive what this means for a t-test, but it basically means the true difference between the groups we think based on this sample could be anywhere from negative 42 to positive 44, which is not very helpful at all. That's because we have like 5 people in this sample, but yeah. So what if you instead wanted to know, so did participants get better from their first score to their second score? So was there a statistically significant improvement in test scores that was different than 0? Because 0 would be no improvement. So in this way, it's a one sample t-test. So you're testing against 0, and all you have to do is call t-test, your data frame, your selector, your variable selector, and your variable. So the difference variable that we created from score 2 to score 1. And then it gives you the mean. So the mean difference was 7.2 points. So that means that on average, people got 7.2 points better on their second test than on their first test. But our p-value is 0.105. So we can't say for sure that like we know that there is a positive difference because our confidence interval crosses 0 here. So we see that our hypothesis was that the scores were different from 0, and our confidence interval encapsulates 0. So it goes from negative to positive. So 0 is in there, so we can't be certain that there is a true difference between the two scores based on this data. Okay, I'll show you just a couple of plotting things, and then we'll move on to the more like tutorial-y part. So you will find that you might need to install and load different packages, and you'll notice sometimes if you try to run a command and it says this function hasn't been found or can't be found. And so you only need to install packages once, but you need to load them each time you restart R. So you can install them using this command, install packages, and then you load it using this command. And also to note, when you're writing a script, you can make comments on the script that won't run, so that won't be executed in the code by using these little hashtags. So note how I've commented this out using hashtags. So plotting is a good example. So there's this amazing package called ggplot in R that has this really like sort of intuitive and easy to use way of plotting things. and it's based on this like graphics grammar syntax, but it's actually pretty flexible and nice once you get the hang of it. So the first thing that you do is basically you call ggplot and you put your data frame here. Then you put in your aesthetics. So your aesthetics are basically going to be what you want plotted where. So in this case, we're making a histogram. So we only want to plot the 2 different sexes by the counts. How many participants do we have in each sex? So this is the first layer. And then you add a plus sign to add additional layers. So you can add multiple layers of different things on this plot if you wanted to. So right now I've added the histogram using the count statistic because some of them do density statistic, but we want count for this one. And then I've just added these labels myself, but you don't have to do that. It will come up if you don't. It just might not be formatted the way you want. And then you also don't need to add a theme, but there are various themes you can add to make this look different, like different backgrounds mostly. Okay. And so, and say we want to actually plot some of the actual data instead of just a histogram. So it's going to be kind of the same thing, except for now that instead of there just being the counts on the y-axis, you want to put the score on the y-axis. So you want to put your sex here, x equals sex, y equals score 1. Then you're going to add what you want to see. So what do I want to see from this data? I want to see the mean, and I want to see it in a bar chart. So I'm going to add a stat summary to this graph. What function am I going to use? I'm going to use the mean. What geom? Geom is basically these little elements that you can add. So if you wanted to add points, it's called geom point. If you want to add confidence intervals, it's error bar. And they're pretty intuitive, and you can just Google them basically, and you'll find what you want to add to this. So I'm specifying the type of geom that I want and the function. Then I also want to add these confidence interval error bars. So I'm going to use these mean CL normal function, which is just the mean confidence level for normally distributed. I think there's like a bootstrapped one too, but you can just use this one most times, I think. And then the width just specifies how big you want this width to be. So it would be fully the width of this bar if I didn't specify that, which looks a bit funny. And then again, I just added custom labels for the labs. Like, yeah. And one thing to note too is that you don't have to memorize all of this, because once you have, once you've built this one graph of this bar chart, basically any bar chart that I build that's going to have 2 groups like this is going to look exactly like this. I'm just going to substitute the data frame and the variables that I want to use. So it might look a little like intimidating, but it's not so bad when you can use your previous code. Okay, so now I think we should move on to this tutorial, but I just wanted to say that my partner wrote an R guide, so I'll send that all to you guys. And it has really detailed instructions about everything. We just ask that you don't distribute it to anyone because we're still working on it, and I think maybe he wants to publish it at some point. I'm gonna try to like hop in there and help. Also, I found this snippet in the guide when I was reading it, and this is directed mostly at Saz and Javita and Blanca from our meeting the other day. He said, plotting a 3-factor experimental design. Seriously, you're manipulating 3 factors in one experiment. I bet you're questioning some life decisions right now. Thanks, Ryan. Lols. Okay. So does anyone have any questions before we move to the tutorial-y part?
No, that was really clear. Thank you.
Cool.
Yeah, thanks.
Okay, now I'm just going to share my R. Okay, can you see this? My RStudio, yeah, cool. Okay. Also, I have uploaded this to our lab GitHub. So I'll just send this link to everyone in the chat, because you can download this script and this data if you want to have a go at, where's my, oh no, well, hold on. Send it if you want to have a go at trying some of this yourself. Okay, you can see this again. Cool. So I basically simulated some data for this. So all this data is made up, but it works for the purposes of just learning how to use R. Okay, so the first thing you're going to do is you're going to, so this is an R Markdown document that I was talking about. And basically the only difference between an R Markdown and R script is that it integrates some different things. So here you can have regular plain text, and then you have your little R components here. So the way you create an R component is you type this, and that creates a section for your R code. So you can basically treat this whole section as if it were an R script. So you can run things in it, but anything that's in this will run. So you need to either comment it out if it's not code, or make sure that it is code that's relevant to your project. But if you want to add words and things that aren't, that won't be run as code, then you can put them outside of the little chunk. Yeah, okay. So like I said before, the very first thing you want to do is install and load all of your packages. So I kind of just put whatever packages I use always at the top for this script. And if I hadn't installed these, I would need to uncomment these lines and install these packages. And if, can you guys see this? Should I just make it larger? Is it really tiny?
Yeah, if you can make it a little bit bigger.
Yeah. Is that better?
Yeah, perfect. Thank you.
When you see everyone being like, it's really tiny. Okay. So yeah, so you're going to install your packages. Then you're going to read in your data. And honestly, this is kind of like a really hard part that was confused me for a really long time. Like, how do I actually get a data file into my R? So as I said before, you want to use a command like read CSV. There are some that are like read Excel as well if you use Excel files, but mostly it should usually be in CSV format. And then you want to name it. So I want to name my data. I'm going to assign it operator to, and I'm going to run this command. And so this is taking this directly from, so this is my working directory here. You can see it pretty much automatically pulls up when you open an R Markdown script from, it basically opens your working directory. So I can see here that I have a data file here and also a data meta file here. So I know that my path to these is just going to be the name of the file itself. Okay, so you can run the chunks either by pressing Command Enter. So I could run it each line like this, and you'll see my data comes up over here, and I can do the same thing there. Or you can run the whole chunk by using this little play button thingy here. Okay, so then you can kind of get a little bit of information about your data here. So you have, in this data set, we have 150 observations, we have 8 variables. In our metadata, we have 20 observations and 7 variables. So let's just focus on this regular data for now, because this is mostly like what you would see if you were doing a regular analysis. Okay, so for example, the psych package has this really nice function called describe. So you can press describe, and it will basically describe all of your different variables and give you the mean, the SD, the median, the min, the max, a bunch of things, the range, skew, kurtosis, SE, for all of the variables that you have. So here you can see we have 8 variables. And I'm pretty sure the star means that these are factors. So we know that group and sex is a factor. This seems a bit of a problem because we know that participant is also a factor. So how would we fix that? Okay, so first I'm just going to check in my data. I'm going to run this class data participant function to see what class my data is. And it's an integer. So I'm like, okay, that's not right. So we want to fix that. So what you can do is you can do the command that basically creates a new variable in your data set, and then type in this function that says as factor, and just basically retype in that same variable again and run that. And then I'm going to check and see if that worked. Did that change my variable to a factor? So let's see. So I run that, and yeah, now it's saying factor. So it changed that variable to a factor. Okay, so then maybe I want to know what are the levels of my factor? Like what is group in this data set? I don't really know. So sex, I'm going to run that, and I can see that it's female and male. And then group, I can run that, and I can see, okay, this is grouped into early adolescence, late adolescence, mid adolescence. So we have 3 groups of people based on their age. Okay, so maybe now I want to know, oh, what age ranges are in these groups, because we also have age continuously in this data set as age. So maybe you want to say, okay, what are the age ranges that they've used to code these in this data? So here I'm going to type range data set, the variable that you want the range of, and then for a condition like we talked about earlier. So for the early adolescence condition, what's the range of age? So I can see here it's 10 to 13. It's giving me the minimum and the maximum. So then, okay, what's the mid-adolescent range? 14 to 17, and the late 18 to 24. So cool. Okay, so now we know a little bit more about the data. And maybe I want to know how many are in each group. So you can do a similar thing here with count. The only thing is you have to add this comma here for sort of complicated reason. But so there's 50 in that group, 50 in that group, and 50 in that group, because I made up this data. So they'll have the same number, but they mostly probably won't. Okay, then a good first thing to do before you kind of start analyzing anything would be to sort of look at the distributions of your data. So I'm going to run these histograms like we talked about before, but I'm going to run it on just a couple of variables just for demonstration purposes. So for age, for depression, and for test score. Also, you can also look at your data if you click on this. It's not a good idea if you have a huge data set, because it will really take a long time. It might crash your computer. But so I can basically see here, okay, I have participant number, I have group, I have sex, age, anxiety, depression, early life stress, test score in this made up data. Okay, so now I want to run just some histograms just to see what it looks like. Okay, cool. So I can see this is my count and these are my ages. So I have some variability in how many people of each age. And my depression as well, but it looks relatively normal-ish. And then test score seems kind of skewed this way a bit. It sort of makes sense if test score is like, you know, the older you get, probably if they're given the same test, the better they might do on the test. Okay. So then maybe we want to know whether the level of anxiety is different between these 3 groups that we have identified: the early adolescence, the mid adolescence, the late adolescence. So since we have more than 2 groups, we need to do ANOVA instead of a t-test like we did earlier. So there's this package called ANOVA, Easy ANOVA or something. It's at the top. And all you do is basically put in your data set, your dependent variable, which will be anxiety in this case, the ID. So what's your participant ID? And then between group, because we want to look at the differences in the dependent variable anxiety between early, mid, late adolescence. Okay, so I'm going to run that, and notice how I saved this as an object here. So I need to run that object again to see the result. Okay, so here's the result. It gives you your effect, your degrees of freedom, 2 by 147, your mean squared error, I think, your F statistic, and your p-value, which is less than 0.001. So we can see that we have a statistically significant difference between our groups. But we don't know which groups are different yet. So we need to do some post-hoc tests. But first, let's just look at the means and see what the means are. So we can do that using this really easy function called em means. you put in the ANOVA that you ran, comma, and then by, as predicted by, similar to the t-test group. And you run it, you save it, and then you run that again. And now you can see the means in all of your different groups. So in early adolescence, it's 75, late is 68, mid it's 84. And then this gives you a confidence interval, an upper and lower bound of your confidence interval. Okay, so that's cool. So it looks like, you know, these have the highest, then early, then late, but we don't know statistically if those are different. So we want to do a post-hoc test. So I'm just going to use a 2 keys test, which is, I think, a common one that people use. And I'm going to just run this command on this ANOVA, on the ANOVA. So the ANOVA saves a bunch of different stuff in here, but you just really want this ANOVA part of it. So that's why you're targeting, that's why you're selecting that part. Okay, so now it kind of does, it does each pairwise comparison and adjusts for your p-value based on how many times you've multiply compared things. So we can see that there is a statistically significant difference, a p-value of less than 0.05 in all 3 of these. So there's a difference between all 3 groups and their level of anxiety. So then we might want to visualize this because it's always helpful to have a plot or a figure when you're reading a paper and you want to see what everything looks like. So say we want to plot the means of, oh, I think I also just want, I think it was saved as a character, so I wanted to make sure that it's, oh, actually, no, this is a different thing. I'll explain that in a minute. Okay, so this is your plot. You're going to enter your data. So we want to do, on our x-axis, we want to separate it by group. So we want 3 groups, early, mid, late adolescence. Then we want anxiety on the y. Then I want to add points for each person. Actually, I'll run this and then show you as I'm explaining. I think it's easier. Okay, I have to like scroll a little bit, but wait. Okay, so this geom point geom basically adds these little points so that we can visualize. It's really good to visualize all your data and not just the mean, because you never know if you have a data point that's way an outlier that's pulling down your mean or up here, or something weird going on. So you kind of, if you can, you usually want to try to visualize all your data points. They are jittered a little bit because otherwise, you know, the x-axis isn't a continuous variable, it's just 2 groups. So in order to see all of these points, you want to add just a little bit of width jitter to the points. Then you want to add a, I wanted to basically add a diamond for the mean so that I can represent the mean on top of this. So it's similar to the way that you add a bar, except for that you call geom point instead. And then you can change the shape of that point to be something different than your regular points if you want to make them seem different in the color and the size. Then I'm going to talk about this line. So then you can add a bar as well, just because some people like bars. It's also, sometimes it's easier to see, like if you take out the bars, it's kind of hard to see necessarily the differences. Like either way, I think you could do this graph with just the points. If you are going to do bars, I would say make sure that it's actually a scale that starts at 0, otherwise it's a little bit strange. And then I also made these bars kind of transparent. So that's, you can control that using this alpha. So an alpha of 1 is completely opaque. An alpha of 0 is completely transparent. So you can kind of play around with like how transparent things are just to make them a little bit less, because this would cover up the dots here if these were black and fully opaque. And then the error bars again are the same as the error bars on the bar chart, and then just a theme. Okay. Okay, I will tell you also now why I did this. So when I originally ran this graph before doing this, mid-adolescence was over here because it does these order based on, I think it's alphabetical. Yeah, so it was early, late, mid, which is weird for a graph of age. So to do that, you have to kind of re-level the factors. So you use the factor command and then you level them in the order that you want them to appear. So I'm basically setting this to level 1, level 2, level 3, so that it appears in that order instead of in alphabetical order. Okay. So then once you get that down, you can do really cool stuff with ggplot when you start wanting to do things like split by sex and look at the data that way. So this is basically exactly the same graph as the one above, except that I added fill equals sex and color equals sex. And so I'll show you what that does. So now we have those bars and those plots exactly like the one above, except for that it's split by male, female, which is pretty cool. And it was so easy. Like I just basically added this one tiny thing to this whole plot code. One thing you do have to note when you're splitting like this, when you're splitting a group into two like this, is that you need to do something called dodging the bars so that they don't go on top of each other. And you basically just add a position for the points I want them to be. So dodging means like moving this way and moving this way. Jittering just means moving like this within. So for the dots, I want them to be dodged and jittered. So I'm going to do position jitter dodge, set the width. And for these are bars, so you can't really jitter them. So I'm just going to set the position to position dodge and the width. Would it be helpful if I showed you how this looks without the dodge so you get what I mean, or do you guys get what I mean? Yeah, show it, or you get what I mean? You get what I mean?
I think it would be helpful to show it.
Okay, cool. Okay, so I'm gonna just set this to 0. Okay, so now they're all on top of each other and they're kind of, oh, these are still dodged. I must have forgot that one. Yeah, I did. But see how the dots are like completely on top of each other and it doesn't really make any sense. So all those dodge is doing is separating them to the two sides of the 3 categories below. If that makes sense.
How do you know how much to dodge them by? So like 0.9.
Yeah, I think it depends. It depends like on how many you have, because if you have a ton, you might want to dodge it like less so that they don't like, and you might want to change the width of the actual bars as well. But ours is pretty good about like it will do relatively decent things with the widths and stuff automatically.
Okay.
But the dodge doesn't really matter. Like it can be whatever you want it to be. Just stylistically, sometimes it looks better for them to be closer together or farther apart.
Yeah.
And then you don't want to dodge them too much either because they might move into the other. If I dodge this too much, it might move over here into this category, which would be strange. Cool. Okay. Now there's just kind of one more type of graph that you might do. Well, that's not true. There's probably a lot, but one of the other major ones that you might do, which is kind of plotting associations. So we've looked basically at means and plotting means of different things with dot plots and with bar charts and things. So now say we want to look at the association between anxiety and depression in the sample. So in some ways, these plots are actually a lot easier than your bar plots because you don't have to specify as many things. So you just feed in your data. You say what you want your X and your Y to be. So I want my X to be anxiety, I want my Y to be depression. I want them to be plotted with points. I want to add a smooth line to plot the line of best fit for all these points. Add my labels and my theme. You'll see what that looks like. So this plot's actually really easy to make because each of these is a person, their score on anxiety, their score on depression. And this line is the line of best fit, the kind of correlation between anxiety and depression in this sample. So you might want to start actually kind of trying to plot these types of things because they are quite a bit easier, even though bar charts are more popular, I guess, like when you think of a basic plot. But yeah, this is relatively simple. And so so we can see that this is a strong, looks like a pretty strong correlation, but maybe we want to test that statistically. So again, doing statistical tests in R is super easy. So in order to do a correlation test, all I'm going to do is type core.test data $anxiety data $depression, and that just tests the correlation between anxiety and depression in my sample. And then I run that. I can see that the estimated correlation is 0.6, and the p-value is really, really small. This is scientific notation, so it's like 0.0016 times 2. And then it gives you all your other statistics to your degrees of freedom, your t-value, your confidence interval of the correlation. So based on this data, we can be fairly certain that the correlation is between 0.49 and 0.69. And then you can do really similar things as you could do with the bar plots, but with your correlation plots. So say I wanted to split it by those groups. So early adolescence, mid adolescence, late adolescence. So I just put color equals group on the same exact plot. And now I have a line for each of my groups. Correlation looks the same-ish in both of them. And I think that's because I forgot to change the correlation in my simulation. But it's kind of cool to look at the different lines like that. You can also do, okay, I just ran a different plot here to show you guys. This is doing age continuously and depression instead of grouped. And you see a similar but shallower kind of association between age and depression. And then you could also split this by sex like we did earlier if you wanted to do that, just by adding this little color equals sex argument there. And then it splits your lines by sex, so you can see what's the correlation in females, what's the correlation in males look like. Okay, then if anyone has to go, that's totally fine. I just thought there's a couple more advanced topics specifically for Yinning and Daryl who are doing the meta-analysis. I was going to go over that at the very end here. So for those who are interested, you can also do linear regression super easily in R. It's basically a more advanced version of correlation. So say we wanted to look at the association between age and depression, controlling for sex and test score. Maybe we thought that sex might have an impact on depression, and maybe this test score was testing something that we thought might be related. So we want to see if that's related to, like, maybe it's your capacity for emotion regulation or something. So doing linear regression is also really easy. You'll see that R prefers like these types of continuous types of statistics over things like ANOVAs in just the way that it's much easier to run them. So I'm going to call it a fit. I'm just going to run a linear model, LM, of depression. And then we have the tilde again, as predicted by sex, age, and test score, and then my data. Okay, so I'm going to run that. And then you can see these are your estimates of your coefficients for each of your variables. So we can see we have a significant association between sex and depression, controlling for age and test score. We have a significant association between age and depression, controlling for test score. And then no real influence of test score. So I just kind of summarize that here. So you can interpret this as we see a significant association between age and depression, such that for every year older a participant is, their depression score is on average 1.21 points higher, holding sex and test score constant. So you get that 1.21 from here, from this estimate. So this can be a nice way to kind of summarize the results of what's in this model here. The intercept is not usually that important. Right now, it represents the average depression score at age 0, holding sex and test score constant, which doesn't really make any sense because we didn't collect any data from anyone under 10 or something like that. So that kind of shows the danger of like extrapolating beyond your sample. Hopefully 0-year-olds don't have any depression. And so then we also see, so another way to, it's a little bit different when you interpret a factor as opposed to a continuous variable. So we see a significant relationship between sex and depression. So on average, males score 6.39 points higher on depression than females. And that's how you would think of that coefficient. So basically moving from female to male increases your score on average by 6.39 points. And then I just like to think about this as like a linear model. So you can really easily predict what score someone might get using this model. So you take your coefficients, your 6.38. For a female, that would be a 0 because you're not a male, because your male is your reference group here. So you put 0 plus 1.21 times 17. So say that they were 17 years old. So I multiply their age by this coefficient here. And then they got an 80 on their test score. And so I multiply that by this coefficient here. So I can predict that a female who's 17, who got an 80 on that test would have an average score of this. And then for males, you can see you do the same thing, but you put a 1 here instead of a 0. And you can see that that's 30.96, which is just 6.39 points higher than the female score for the same age and the same test score. You can also calculate the standardized regression coefficients, which are called betas, using the LM beta package, which I think is really useful. What a standardized beta is, if you don't know, is it compares the strength of the effect of individual independent variables to the dependent variable. So in other words, they're the coefficients that you would get if the variables in the regression were all converted to z-scores before running the analysis. So basically, it just means that you can compare the strength of the variables with each other. So, and that really depends on the scale. So like say you had a scale that ranged from 0 to 60 on test, but then say your like, your male female is only from a 0 to a 1. So moving on that might create a smaller, like moving 1 point on your larger scale might not have as much influence, but it might actually be more important, if that makes sense. I'll show you what I mean with this beta thing. So here's your regular estimates, then here's your standardized estimates. So we can see here that even though this estimate of age is smaller than this estimate, it's actually, the standardized estimate is larger. So it's more contributing to this model than sex is, if that makes sense. Okay. And then I'm just going to show a quick meta-analysis thing for Yining and Daryl, who are doing a meta-analysis, which actually turned out to be really straightforward. So if anyone else wants to hear about it. So I simulated this data for a meta-analysis saying that we have 20 papers by 20 different authors. And say, so for this, we're just going to pretend like we recruited a bunch of participants who had a depression score in a certain range for a new intervention or something. So half of these people, they all kind of start at the same general level. We're going to randomly assign half of them to this experimental condition, and we're going to assign half of them to a control condition, a different treatment, perhaps. Then we're going to do the treatment. Then afterwards, we're going to take their average score after the treatment. So this was the mean of the experimental group in this study and the standard deviation, which you can usually get from the paper or the data. And then you also need to know how many were in that group. So there was 53 people in this author's experimental group with this average and this standard deviation. And let's, like for the purpose of this, all these authors are testing the same intervention against the same kind of control intervention. So yeah, so you need this information for both of the groups for each study. You need the N's, you need the SDs and the means. And then you can perform a really easy meta-analysis using this cool package. So this was just a function to kind of look at your data to see what kind of data are in there, but we looked at it this way. So here, you're basically just putting in, you're just letting this function know what your variables are called. So what your experimental N is what your experimental mean is, what your experimental SD is, and you need to put it in this specific order so that the function knows what to do with it. You tell it where your data is, you tell it what your, your participant ID kind of is, which in this case is the author. This is whether you want a fixed or a random effects model, and I think you mostly usually want a random effects model for this kind of thing. It's assuming some kind of equal variance between studies, which I think is not often met. And then the kind of type of method that you want to use and the type of effect size you want. So you literally just run this, and you can basically just leave, you can pretty much leave these the same for most studies if you're just wanting to use a basic random effects meta-analysis, and just change these so that they're your variables that you want. You run it, and then you literally just type forest meta model, and it gives you this really cool meta-analysis thing. So basically what this is for each study, it's kind of summarizing what we saw in the table. Then it's telling you what the effect size is for each one of those studies. So the experimental group reduced depression in all of these studies because these are less than 0. In these 3 studies, it was the opposite. So the control group had lower than the experimental group. But on average, we think that the average effect of this treatment is negative 1.5. And because the confidence interval here is not crossing 0, we can say that we are pretty sure that the true estimate of the effect size of this intervention lies between negative 1.62 and negative 0.67. And this is something else called the prediction interval, which I'm not entirely clear on. I think it's like the range of values that you might expect to ever see or something like that. I don't know if anyone knows. But yeah, so that's pretty, and then it gives you the effect size for each study and its confidence interval, how much it's weighted by the number of participants that you have. And then, yeah, this is the effect that you would want to report here, the average effect size and its confidence interval. So yeah, that's pretty much it. That's all I have. Does anyone have any questions? Comments? Thoughts?
That was really helpful. Thank you, Emily.
You're
It was
welcome.
really good, thanks.
I hope it was helpful.
Yeah, it was pretty helpful. I might ask at some point. I was trying to install the stuff on the GitHub, and I got a lot of error messages. So I think you said you were going to send around some material, so I'll work through that, and then I might need to ask if it's still not liking me. I've probably done something wrong, but
Yeah. I feel if anyone has any questions or needs help, I'm totally around. I helped a friend the other day figure out why she couldn't read in her file, and it was like the funniest, but she's like not a computer person. It was the funniest, but also like only funny to me because she didn't even know. It was like it was an Excel file that she had named CSV file.
Oh, wow.
Except for, I think it was CVS even. I think it was CVS file. And I was like, this is really funny, but oh dang, I just recorded that. Now she's gonna be mad at me. Stop recording. Okay, how do I